In this video, we're going to put together what we've learned about first and follow sets to construct LL1 parsing tables. Our goal is to construct a parsing table T for a context-free grammar G. And this is done by production. So we're going to do this one production at a time. And we're going to, in turn, consider each production A goes to alpha in the grammar G. All right, so the first case is if we are trying to figure out whether we can use A goes to alpha and T happens to be in the first of alpha. All right, so if we know that some terminal T is in the first of the right-hand side, then if we were in a situation where A was the leftmost non-terminal and T was the next token of input, then expanding by A goes to alpha would be a good move because the alpha could potentially, through more productions, match the T. And so we'll add to the parsing table at the AT entry the right-hand side alpha. All right, the other situation that we're interested in is what if we need to get rid of the A? Okay, so if the A cannot possibly match the T, all right, so let's say the T is not in the first of alpha, or we have some other situation where we want to erase the A, well, then it would be okay to use production A goes to alpha, provided that alpha can actually go to epsilon, so alpha can go away completely, all right, so we can eliminate all trace of the A. And T follows A in the grammar. So T is able to come after, T is able to come after A in some derivation. So if T is in the follow of A and the right-hand side of the production can go to epsilon, then we add the move that when A is the leftmost non-terminal and T is the next input, we can expand A by A goes to alpha. And finally, a special case for $, because $, is technically not a terminal symbol, if we're at the end of the input. Okay, so we have some stuff left on the stack. In particular, we have the non-terminal A is still our leftmost non-terminal, but we've run out of input. Well, then our only hope is to get rid of the A completely, and so we want to pick a production for A that can go to epsilon. So we look for a production A goes to alpha where epsilon is in the first of alpha, and $, can follow A in a derivation. So that is the procedure, or those are the rules for constructing a parsing table. And now let's work through an example. So here's our favorite grammar that we've been looking at for the last few videos. And now let's take a look at what the parsing table will look like. All right, and the parsing table will consist of columns that are labeled by the terminal symbols of the grammar. All right, so here we'll have open paren, close paren, plus, times, and int. And then the rows will be labeled by the terminal symbols. So we'll have E, T, X, and Y. All right, and now we're just going to take each production and apply our rules and see what entries in the table we create. All right, so when would we use E goes to TX? All right, well, so the first thing to observe about this production is that it cannot produce epsilon on the right-hand side. So TX always produces at least one terminal, and so the second case where we're interested in whether the production can go to zero, as it could go to epsilon, is not going to apply. All right, so we just have to consider what it can generate in the first position. So the only things that this production can generate in the first position are things that are in the first of T, which are open paren and int. So there are two situations in which we'll use the production E goes to TX. That is if E is the leftmost non-terminal and the next input is an open paren. Okay, and the other one is that if the next input is a int. Okay, so now let's take a look at this production. All right, so when are we going to use T goes to open paren, E close paren? Well, if T is the leftmost non-terminal, all right, that's the symbol on the left-hand side, and an open paren is the next symbol in the input, okay, because that's the only thing in the first of this right-hand side, then it would be a good move to expand by open paren, E close paren. So there's only one situation where we use that production. All right, and for the other production, the other T production, we're going to use that when T is the leftmost non-terminal and there's an int in the input. So over here, we'll have int y, and I forgot one column over here for $. Okay, so we'll stick $, in there at the very end. Okay, so now we've covered these first three productions. Let's take a look at this production. So when would we use x goes to plus e Well, clearly the only thing in the first of the right-hand side is plus, and the symbol on the left-hand side is x. So the x plus entry, we would want to expand by x goes to plus e. And similarly for y, the first production involving y, when y is the non-terminal we're trying to expand, and there's a times in the input, we would use the production y goes to times t. Okay, and now we just have the two epsilon productions left, and these are the only productions actually that can go to epsilon. And so when would we use x goes to epsilon or y goes to epsilon? All right, so recall that we need to know what is in the follow of x in order to know when to use x goes to epsilon. And we computed that in the last lecture, but let's just write it down again here. Okay, and so what was in the follow of x? Well, we had to look at where x was used in the grammar. X was used there. It appears at the right-hand side of the production, so it would be things that were in the follow of e. What was in the follow of e? Well, e is the start symbol, so dollar is in the follow of e, and close paren is in the follow of e. All right? And then what was in the follow of y? That's the other one where we'll need to know the follow set. Again, we have to look at where y is used, so y is used there. That means everything that's in the follow of t is in the follow of y. The follow of y will therefore include the first of x, because x can come after t, so plus will be in the follow of y. All right, but then x can go to epsilon, and so everything that's in the follow of e will be in the follow of t, and therefore also in the follow of y. So the other two things in the follow of y were $sign and close paren. All right, and so what this is saying, okay, is that if we are in a situation where we have an x, okay, let's just focus on the x goes to epsilon production for a moment. Let's say that we have an x on the stack, okay, at the top of the stack, and dollar is our next input. Well, what can we do? We're at the end of the input, and we have to get rid of the x, so obviously we want to use the x goes to epsilon move. Okay, so that makes sense. And the other situation, the follow set tells us to use x goes to epsilon is if there's a closed paren on the stack, because the x cannot generate a closed paren by itself, but hopefully some other symbol that's on the stack will be able to generate it once we get rid of the x. Okay, so we should also use x goes to epsilon in this situation. Right? And then similarly for follow of y, or for y goes to epsilon, that production, there are three things in the follow, three terminals in the follow of y, and we should use y goes to epsilon if they are the next thing in the input. So if we see a plus and we're trying to expand to y, we'll use y goes to epsilon. If we see a closed paren and we're trying to expand to y, we'll use y goes to epsilon. And finally, if we're completely out of input and we still have a y left over, we'll use y goes to epsilon. And that is the complete parsing table. All right? And now you can see how this will work in every situation. Okay, for our leftmost non-terminal and for every possible input or lack of input, we have a production that we can use. And now there are a lot of blank entries in this table, and what do those correspond to? Let's say that we were trying to expand x, and the next input symbol was a open paren. Well, there's no entry here. Okay, and so that's an error. That's a parsing error. And so whenever you encounter a blank entry in the table, when you try to use a blank entry when you're parsing, that's going to generate a parsing error, because what that tells us, the fact that there's a blank entry, it tells us that there is no valid move. There is no way that we could parse that string. And we discover that at the point where we try to access an error or blank entry in the table. So now let's consider what happens when we try to build an LL1 parsing table for a grammar that is not LL1. And let's take a look at the simple left recursive grammar that we have looked at before. So S goes to SA is one production, and S goes to B is the other production. And to build the parsing table for this, we'll need to know the first and follow sets. So let's take a look at the first of S. All right, so what can S produce in the first position? Well, it can clearly produce a B, and there's no epsilon, there's no possibility of generating epsilon from S, and so in fact that's the only thing that's going to be in the first of S. And what about the follow of S? What can follow in S? Well, it's the start symbol, so clearly dollar is in the follow of S. And then the terminal A appears right after S in the first production, and so A is also in the follow of S. And now we're ready to build our table, and it's going to be a very small table. We only have one non-terminal, and then we have two terminals, A and B, and we have the end of input symbol. So it's just 3 entries potentially in this table. All right, and so now let's take each production and see where we should put it. So let's just take a look at the second production first, because that's, well, for no particular reason. So we have S goes to B. When should we use that? Well, clearly, if we see a B in the input, this would be a good one to use, because the first of the right-hand side includes B. All right, so S goes to B would be used if we see a B in the input. And now what about S goes to SA? Well, here, again, this can't generate epsilon, so we're only interested in what it can produce in the first position. And once again, the first of S is just B. And so we'd also have the move, in the SB entry, we would have the move S goes to SA. And now we see the problem, right? Here we have an entry that has multiple moves. This is a multiply defined entry. Okay. And what does that mean? Well, that means if we see an S if we have an S that we want to expand, okay, we're trying to, if S is our leftmost non-terminal, so at the top of the stack, and B is our next input symbol, all right, this table doesn't tell us exactly what move to make. It's not deterministic. It says there's 2 possible moves that we can make. And so this is how you know a grammar is not LL1, because if it winds up that you build the LL1 parsing table and then you have more than one entry, more than one possible move in some position in the table, some entry, excuse me, I use the word entry incorrectly. So if you wind up, let me say that again. If you build the table and some entry in the table has more than one move in it, then there's not a unique move for every situation for the parser, and that grammar is not LL1. So as we just said, if any entry is multiply defined in the parsing table, then the grammar is not LL1. And in fact, this is the definition of an LL1 grammar. So the only way to be sure that a grammar is LL1, or the mechanical way to check that a grammar is LL1, is to build the LL1 parsing table and see if all the entries in the table are unique. Now, that we do know, however, that there are certain classes of grammars that are guaranteed not to be LL1. And what are some of those? Well, any grammar that is not left factored will not be LL1. Okay. Any grammar that is left recursive will not be LL1. Okay. And any grammar that is ambiguous is also guaranteed to not be LL1. But this is not an exhaustive list. Other grammars are not LL1 too. So in particular, if a grammar required more than one token of look ahead, it would not be LL1. But even that isn't a complete list. There are even grammars beyond that that are not going to be LL1. So what this amounts to, these 3 things here, amount to quick checks that you can do to test whether a grammar is guaranteed not to be LL1. But if just because a grammar is left factored and it is not left recursive and it is unambiguous, that doesn't guarantee that it's LL1. And the only way to know for sure is to construct the parsing table and see if all of the entries in it are unique. And unfortunately, it turns out that most programming languages, their context-free grammars, or the grammars that describe most programming languages, are not LL1. And the LL1 grammars are too weak to actually capture all of the interesting and important constructs in commonly used programming languages. And there are more powerful formalisms for describing grammars and or practical grammars, and we're going to be looking at those in future videos. It turns out that they build on everything that we've learned here over the last few videos for LL1 grammars, so none of that will be wasted, but they assemble those ideas in a more sophisticated way to build more powerful parsers.